everyone, my name is Bono Isaac Berry, and today I'm going to show you a circle with all the trigonometric identities and talk about similar triangles a little bit. Now, I know it's been a long time, but I really have nothing else to do and I need to do something related to math. So I'm back to my math lectures as always. So this is a pretty famous diagram, but most people who do it don't explain how it works. We have sine theta, cosine theta, and tan theta, along with cosecant theta, secant theta, and cotangent theta. Now, for these two, the definitions are pretty set in stone, but for the other four, you might not have received the most intuitive definition. For example, you might have learned this one is the ratio between sine theta and cosine theta. But there's also a geometric facet to this. So, let's draw it. First of all, let's get to the point by naming this O, because this is the center of the circle, and O is the character that looks most like a circle. So, let's make it more apparent. So this is O, and we're going to draw a line that intersects this circle at P. So this is going to be a unit circle, and let's call this Q. So this has length 1, this also is length 1. And let's call this theta. So first of all, what's this angle? Well, we'll think about that later. But for now, what I'm going to do is I'm going to draw the perpendicular from P to this line. And I'm going to name their point of intersection R. So that means that we're defining this to be 90 degrees by default. So that means if this is theta, then this is 90 minus theta, or pi over 2 minus theta if you're a radians user. And since this is pi over 2 radians, then that would make this exactly theta radians. So that's about that. Now, that also presents us with the pretty interesting fact that you can draw this parallelogram right here, which asides OR, OP, and I guess you would have to make another S with RS and PS. But regardless, this is an interesting fact that definitely shows us that cosine of pi over 2 minus theta is equal to sine theta. It's also 0. So, am I doubtful of this? I probably am. So let's check one more time. So I'm going to work in degrees for this one because that's how I naturally do things. No, it seems to work just fine. And I think both are true, actually. Yeah, both are definitely true. I'm going to show the result that OPS is similar to SPQ. So, how can I do that? Well, good question. What we are going to do is, I should probably put a new thing, T, okay. So, basically what we're trying to do here is we're saying if we have a right triangle, I will just call it ABC here, and we draw the altitude from B to AC, then how do we prove that here ABD and BDC are similar? And later we'll also prove the same result that both of them are similar to ABC. So this is going to be theta. This is going to be, I'm going to use radians, pi over 2 minus theta. And since this is already pi over 2, that means this has to be theta as well. So the same case applies over here, pi over 2 minus theta. So I think it's pretty clear. We have theta, pi over 2 minus theta, and an angle, a right angle. Then we have another right angle, pi over 2 minus theta, and theta. So I think that should show that here triangle ABD is similar to triangle BDC by AAA. And this is going to be sine theta, and this right here is going to be cosine theta. And now we draw the big boy. Now we draw the tangent at P, which is going to be a little tricky, but we have more horizontal space than vertical. So we can do this one. So yeah, there we go. And let's say it lands at S. This is now tangent theta, and I've already proved that these two triangles are similar. I've probably also forgotten to denote this theta. What are we going to do next? Well, how do we prove tan theta is sine theta over cosine theta then? Well, it's related to the similar triangle proposition. You see, this angle is pi over 2 minus theta. How did I get to that point? Well, it's pretty simple. We have a total of pi radians. That's the sum of all these three angles. I hope we know that by now. Then we have this angle, angle POR, which is already theta. And then we have, so we have pi minus theta minus pi over 2. So this has to be what's left. And that's just pi over 2 minus theta, which makes sense, doesn't it? And now, for the same reasons, this angle too is pi over 2 minus theta, given that this is a right angle. So now we've established these two similarity. So what can we do now with that information? Well, let's bring the cosine theta down to here. Here's the thing. Corresponding parts of congruent triangles are congruent, and similarly, corresponding parts of similar triangles are proportional. So, this isn't an official theorem name, but I just came up with it on the spot. But it's still true. So, that means that, what do we mean by corresponding side? Well, the corresponding side to cosine theta in this triangle is sine theta in this triangle. How do I know? Well, what's opposite to pi over 2 minus theta here? Cosine theta. What's opposite to pi over 2 minus theta over here? Sine theta. So we use that technique all around the place. That's what we mean by corresponding corresponding sides. So that means tan theta corresponds to this length, which I should have mentioned is 1 because it's a radius of the bigger circle. So we know that we have a proportion to 1 over tan theta is equal to, well, what do we have now? We actually know, we don't know this part. We can obviously find it, but that's easier said than done. So now we have pi over 2 minus theta is opposite to sine theta already, and we know pi over 2 minus theta is opposite to cosine, so we draw the same ratio here. And there's a reason it's not sine theta over cosine theta instead. It's because these two are from the same triangle, and these two are from the same triangle. So now we just reverse this, and it gives us the ratio that we all know and love. We proved it right. So now, let's talk about the other ones. So now, we've already crossed off sine, cosine, and tan. So we have to get to their inverses pretty quickly now. Now the first one is hiding in the diagram that we already have. It's this pesky fellow, OS. Now how do I prove that? Well, remember what I said ABC is also similar to all of these by AAA? Well, we can use that to show this with the same CP-STP thing. So, we have this length is 1 with the whole thing, and so this is opposite to the 90-degree angle. Don't talk about that. And then this length that we're trying to find, and I'll call that D for right now, is opposite to the right angle. And then we have the other way. Let's pick one of these. We know that pi over 2 minus theta is opposite to cosine theta. And in the real thing, pi over 2 minus theta is opposite to 1. So 1 over d is cosine theta over 1, which leads to d is 1 over cosine theta, also known as secant theta. I can't believe it was hiding in thin air all this time. So, as you can see, this whole length was secant theta. So, now let's find the, I crossed off the wrong one. Now let's find the other two. They're all hiding in another triangle, namely this one. Extend this line SP all the way to the line OQ, and we get the intersection point P. In this triangle, again, OPT is similar to all the other ones by AAA. All of these 7 triangles that we've now created with that one touch are similar. It's actually maddening. Well, not maddening, but delightful. I don't know what to say. So now, how do we figure out the dimensions of this little fellow right here? We already know this is theta, this is pi over 2 minus theta. I've shown you the techniques for it long ago, so you should be able to infer now how this works. And now, we have this other triangle. We all know that OQ and PR are congruent. This is definitely a rectangle because of all the right angles. We have sine theta. That's weird. Do I have a sore throat? We have sine theta, cosine theta. And then what's this length right here? Or rather, what's this length right here? Well, that's a pretty good question. This is 1, by the way. I should write that. So, we're going to take the similarities between this triangle and the big boy, OPT. So this is theta, and this is right angle. So that's a little bit daunting, but let's get it over with. So here, theta is opposite to 1. That's for the big triangle. For the small triangle, theta is opposite to sine theta. And here, we're trying to find this one. So here, the hypotenuse is opposite to, 1. And here, the hypotenuse is opposite to the thing we're trying to find, OT. So, question mark over 1, which is really just OT over 1, is equal to 1 over sine theta. In other words, yep, we found another sneaky boy. Oopsie daisy. Oh God. This right here is cosecant theta. Sorry, I botched that. And now, time for the final villain reveal. Wow, this is truly beautiful. But we have the big boy, OST. Isn't it so beautiful? And for the largest length in this entire triangle, in this entire diagram, TS. What could that be? Well, I wonder. Thank goodness we can use this convenient thing. So, we have cosecant theta and secant theta. Here, we have sine theta and secant theta minus cosine theta. That's not going to work. Here, we have sine theta and cosine theta. So now, what are we going to do? Well, this is 1. So, this purple thing corresponds to this purple thing. No, I should have made this red. But this red thing corresponds to that red thing. So, sine theta over secant theta is equal to cosine theta over cosecant theta equals tan 1 over the big boy. So for the final reveal, sine theta over secant theta is 1 over OT. So OT should be secant theta over sine theta. Wait, something's fishy with that. Something's a little fishy there. Oh shoot. Shoot. I got them out of order. Let's try that one again. Shoot. If I got them out of order, what can I do instead? Well, there are not many good triangles because a lot of them, like this one, involve subtraction, and that's going to make our stuff nasty. So, instead, let's try using this one again. I'm not sure what went wrong that time. So, yeah. So, cosine theta is opposite to pi over 2 minus theta, and 1 is opposite to 90 degrees. Here, pi over 2 minus theta is opposite to cosecant, and the big angle is opposite to the big boy. I'm starting to get worried again, because this means cosine theta is equal to 1 over OT. That does not seem right. That can't be right. Cotangent theta has eluded me on this diagram after all this time. Well, it's probably PT, so let's go for that one instead. Let's see if that can finally salvage this and put this dumb story to rest. Cosine theta, I found a completely unrelated sine theta times cosine theta thing here. So here we have cosine theta is opposite to theta, and sine theta is opposite to theta. And here we're opposite to 1 with 90 degrees. And here, oh, yep, that was cotangent. Oopsie daisy. So the final villain reveal was, okay, so the final villain reveal was really not of substance. That's cotangent theta, and that's final. We've crossed off all 6 of them, and the diagram is done.
Can you circle all 6 trigonometric identities?
Yeah, well, that's why I color-coded them all. I hope it'll be easy to spot now. So, cosine theta sine theta, secant theta, tangent theta, cotangent theta, and cosecant theta. Those are the 6 trigonometric identities. Thank you everybody for watching.